Hi, in this video, we are going to look at congruences. And this is the third video for our number theory section. And let's begin with the theory for congruences. So we start off with a basic definition. Let m be a positive integer. M is a positive integer. And A and B are integers. In that case, if m divides A minus B, then we say that A is congruent to B modulo M, mod M. So this is the definition of two numbers being congruent to each other modulo M. So what is the meaning of that? The M should be able to divide A minus B. Or you can say, in other words, if A is congruent to B mod M, then both A and B leave the same remainder when they are divided by M. When they are divided by M. Also, if M does not divide A minus B, then A is not congruent to B mod M. So that's how we define the basic congruency. Now, we have some nice properties of congruences which are very similar to the normal ways in which we operate with numbers. So I will list down some of these properties. So for a fixed modulo M, these are some of the properties that you can say. First of all is reflexivity. Reflexivity basically means that A is congruent to A mod M. It is obvious because M will divide A minus A. A minus A is actually 0. So M divides 0. So reflexivity is true. Similarly, symmetry is also true. Symmetry means that if A is congruent to B mod M, then it implies that B is congruent to A mod M. This is true because M divides A minus B, so obviously M will also divide B minus A with a negative quotient, right? The third property is transitivity, transitive behavior. So if A is congruent to B mod M and B is congruent to C mod M, this implies that A is congruent to C mod M. So if A is congruent to B, B is congruent to C, it implies that A is congruent to C, right? The fourth property here is if A is congruent to B mod M and C is congruent to D mod M, then A plus minus C will be congruent to B plus minus D mod M. All of these properties, by the way, can be proven by the definitions. So we know that here A is congruent to B mod M means M divides A minus B. Similarly, M divides B minus C. Now you can easily show that M will divide B plus minus D minus A plus minus C. That is very easy to show because you can write A minus B as some Tm and D minus C as some Sm, where T and S are integers. And obviously now you can say that D plus D minus A plus C, you can take a combination of these to construct D plus C minus A plus D. And you'll get a new integer and you can show that M will divide this also, right? So if you have two pairs of numbers that are congruent to each other, then you can basically make combinations of them and they will be still congruent to each other, as long as you stick to the same operation, right? You're doing A plus C, it is congruent to B plus D mod M, right? Okay. The next property is this one. If A is congruent to B mod M and C is congruent to D mod M, this implies that AC is congruent to BD mod M. So not just addition and subtraction, multiplication also holds normally under congruence operations. So again, the proof of this is very easy. You can do it yourself. Next property is this. If A is congruent to B mod M and K and C are integers with K greater than 0, then we can say that A power K multiplied by C will be congruent to B power K multiplied by C mod M. The proof of this also can be shown using the standard definition. It is not very difficult to get that. One thing that does not normally hold true is the cancellation law. So the cancellation law that we see normally when we use numbers doesn't actually apply in congruences. So AC is congruent to BC mod M does not necessarily mean that A is congruent to B mod M. You cannot cancel C from both sides of the congruence without thinking about it. So there are some situations where it is true. The situations are when GCD of C and M is 1. So actually, the real law here is if AC is congruent to BC mod M, it implies that A is congruent to B mod M by Cm, GCD of C and M. Now, if GCD of C and M is 1, or basically C and M are co-prime, then this boils down to this, right? A is congruent to B mod M, and then the cancellation loss works normally. But in other cases, when C and M are not co-prime, you will have to be satisfied with this statement. So remember that the cancellation law does not apply as per usual. The next property that we look at here is this one, property 8, which is if A is congruent to B mod M and D divides M. So D is a divisor of this modulo M, right? Then we can say that A is congruent to B mod D as well. So if you have, for example, 5 is congruent to 11 mod 6, right? As an example, we know that 5 and 11 are congruent to each other mod 6. So then we can also prove that 5 will be congruent to 11 mod 3. Notice that 5 is actually 2 mod 3 and 11 is also 2 mod 3. 3 is a proper divisor of 6, right? So this is an example to show this property, right? This is property 8. Then we look at the next one, which is if A is congruent to B mod M and D is not equal to 0, then we can say that D times A will be congruent to D times B mod D times M. So you can go in the forward direction, but you cannot cancel without thinking, right? So the forward direction works. You can multiply everything with D here, and this equality is true. But the reverse direction is not necessarily true. It will be true only if, obviously, here this is mod dm and here it is mod m. So it doesn't have to be true. The next property is this one. If A is congruent to B mod of mi, where I can go from 1 to k, right? Then A will be congruent to B mod of the LCM of all of these mi's. This symbol, the square bracket symbol we have discussed earlier, stands for LCM. So here what we are saying is if A is congruent to B, let's say mod 3, and then A is congruent to B mod 5 also, then A and B will be congruent to each other even for mod 15, where 15 is the multiple of 3, LCM of 3 and 5, right? So these are the basic properties of congruences. Each of these can be proved using the definition of congruences. Now, we have listed down these 10 properties. We will go to try to understand something called residue system, and then we'll come back to these properties and tell you a couple more nice, interesting properties. So first we'll go over to residue systems. We'll try to understand what we mean by that. So this is a very important section. Please focus on this. So the idea is this. The set of integers from 0, 1, 2 till n minus 1 is called the least residue system. Least residue system modulo n. Now, what do we mean by that? Any set of n integers, no two of which are congruent to each other, modulo n, is called a complete residue system modulo n. It's called a complete residue system modulo n. So first of all, what is this residue? Residue is another way to say remainder. So if you divide any integer by n, these are the possible remainders, right? 0, 1, 2 till n minus 1. So there are n possible remainders. So if you have any set of n integers, no two of which are congruent to each other modulo n, basically, if no two of these n integers are congruent to each other, then that means that they will all have different remainders when you divide them by n, right? So since they have all got different remainders, these remainders must be from this set, right? These remainders can only be 0, 1, 2, or n minus 1. So there are n possible remainders. So therefore, any set of n integers where none of them are congruent to each other basically make up a complete residue system modulo n. We call it a complete residue system because it covers all the possible remainders when you divide these numbers with n. There is no remainder that is missing. There has to be some integer here which has a remainder 2. There has to be some integer in this group which has a remainder n minus 1 and so on. So therefore, it is known as a complete residue system modulo n. Okay, so for example, let's look at some examples here. So the least residue system modulo 4 is basically 0, 1, 2, 3 is this set. These are the least possible remainders and all the unique remainders that you get when you divide any number by 4, right? Now, there are other ways to write this. We can say 13, 14, 15, 16. What is this? This is a set of 4 integers, no two of which are congruent to each other, modulo 4, are congruent modulo 4. And since we have 4 integers, none of which are congruent to each other modulo 4, this is a complete residue system modulo 4. Complete residue system modulo 4. Right? Now, another example of this could be -2, -1, 0, and 1. Think about this. These are also complete residue systems modulo 4 because the remainder of -2 when you divide it by 4 is basically, it is simply 2 modulo 4. And this is 3 modulo 4, and this is 0 modulo 4, and this is 1 modulo 4. So this -2 corresponds to this element, -1 corresponds to this element, and 0 and 1 correspond to these two elements. So this is also a complete residue system modulo 4, right? So that is your idea of complete residue system modulo 4. Now, what we look at is the Euler's phi function. So I feel like I have introduced this before, but in case I haven't, I'll just talk about the Euler's totient function for the phi function, and then I will talk about the reduced residue systems, right? So I'll just define the phi function here. So phi of m basically is known as the Euler's totient function. It is the set of all integers less than, all positive integers less than m that are co-prime with m. Co-prime with m. So what is the meaning of this? For example, phi of 3. What are the integers less than 3, positive integers less than 3 that are co-prime with 3, right? So obviously 1 is co-prime, 2 is co-prime with 3, and that's it. So this is phi of 3 basically is 2, right? So the value of phi of m is the count of the number of integers less than m which are co-prime with m. So I have made a slight error here when I'm saying it is the set of all positive integers. What it is the cardinality of that set. Phi of m measures the number of elements in this set, right? So you can see phi of 7, for example. Phi of 7 would be all the positive integers that are less than 7 and co-prime with 7, right? So 1, 2, 3, 5, actually 4 also, and 6 also, right? So there are 6 integers here, all of which are co-prime with 7, and they are positive integers. So phi just counts all the possible co-prime positive integers less than m, and phi of m has some nice properties. So for example, if it is a prime number, if p is prime, phi of p will always be p minus 1. You can say the examples, phi of 3 was coming out to be 2, phi of 7 came out to be 6. You can take the example of phi of 2. 2 is a prime. The only integer less than 2 that is positive and is co-prime with 2 is 1. So phi of 2 is also 1. So for prime numbers, this is the situation. You also have a multiplicative property. Phi of mn is same as phi of m times phi of n. So the phi of m function is a multiplicative function, and we will see some more properties of this totient function as we go along. So for example, we can say that if m is greater than 2, phi of m is an even number. Phi of m will be an even number. Think about it. For all primes, we already know phi of p is p minus 1. So all primes are odd. So all of this is becoming even, right? Because odd minus 1 will be even. Correct. So for example, if m can be factorized like this, p1 power alpha 1, p2 power alpha 2, till pk power alpha k, then the phi of m here is the set of integers co-prime with m less than it will be equal to m times 1 minus 1 by p1 multiplied by 1 minus 1 by p2 and so on till 1 minus 1 by pk. This is the formula for phi of m if you know the standard factorization of that number, right? So if you can factorize the number, you can count the number of co-prime numbers to it by this formula. And also, if m and n are co-prime numbers, I mentioned this property before, phi of mn is simply phi of n times phi of n. This is the multiplicative property of this Euler's function. Now, why do I need this Euler function? Because now we'll define something called the least residue system or reduced residue system, where we need to understand this property. So reduced residue systems. What are these? So any set of phi n integers, any set of phi n integers that are relatively prime to n, that are relatively prime to n and are mutually incongruent under modulo n is called a reduced residue system. Is called a reduced residue system mod n. System mod n. So what is this? So let's get into the details here a little bit. A subset R of integers is called a reduced residue system if it satisfies the following properties. If it satisfies the following properties, first of all, GCD system mod n. First of all, GCD of R, small r and n must be 1 for all small r belonging to capital R, right? So any integer that belongs to this subset must be co-prime with the modulo n, with n, right? So it must be co-prime with n. Second property is R should contain phi of n elements. So R only contains phi of n elements. The total number of elements is the number of elements, number of numbers that are co-prime to n, right? And finally, no two elements of R are congruent to each other modulo n. Are congruent modulo n. So elements of the subset R cannot be congruent to each other. The total number of elements in that subset must be equal to phi of n, and every element of that subset must be co-prime with n. If these three criteria are satisfied, then that subset is known as a reduced residue system. So I will give you some examples. So if you take a complete residue system, what was a complete residue system? Let's say we want to find complete residue system mod 12. So what does this mean? This means that when you divide by 12, what are the possible remainders that are allowed? And all of them have to be part of this set, right? So the all possible remainders are 0, 1, 2, 3, 4 till 11. Right? 7, 8, 9, 10, 11, 12, right? These are all possible remainders when you divide by 12. So this is the complete residue system mod 12. Now let's think about what is phi of 12, right? Now phi of 12, since 3 and 4 are co-prime with each other, the GCD of 3 and 4 is 1. So we can use the multiplicative property and say that it is 3 into 4. So it will be equal to phi of 3 into phi of 4, right? And now phi of 3 is a prime. So that will be 2. Phi of 3 will be 2 because phi of prime should be p minus 1. And for phi of 4, we will use the formula. Now, the formula was m was equal to p1 power alpha 1, p2 power alpha 2, and so on. Then phi of m was equal to m into 1 minus 1 by p1, 1 minus 1 by p2, and so on, right? So if you use this formula, 4 is simply 2 power 2, right? So phi of m should be equal to 4 into 1 minus 1 by 2. And then there is no other prime here, right? So it is 4 by 2, which is 2, right? So we are getting by the formula 2 into 2 is equal to 4, right? Obviously, we could have figured out phi of 12 just by listing out the terms. But I wanted to show you how to use these calculations. Right? These results that we had seen, we are using them to calculate that phi of 12 is 4. Now, which ones are part of the reduced residue system? Reduced residue system. So if you want to construct this modulo 12, this set here, we know that it has to have 4 elements. That was the second property, that the set R must have 4 elements. Which 4 elements? It has to have any element of R here must be co-prime with 12, right? So we can say 1 is part of it, 1 is co-prime with 12, but 2 cannot be taken, 0 cannot be taken, 3 cannot be taken, 4 cannot be taken, because these are not co-prime with 12, right? 5 can be taken, 6 cannot be taken, 8 cannot be taken, 10 cannot be taken, 9 cannot be taken, because they have factors, 3 and 2 and so on, right? So we have 1, 5, 7, 11, and 12 cannot be taken. So only 4 numbers which are co-prime are 1, 5, 7, and 11. So this is the reduced residue system mod 12. You can notice that all of these numbers, all 4 of these are not congruent to each other. They are all co-prime to 12, and they are a subset of the complete residue system, right? So that is the idea of this reduced residue system. Now, obviously, this is not the only way you can write the reduced residue system here. Some alternate ways to write the reduced residue system mod 12 would be 13, 17, 19, 23, for example. Why these? Because if you see, 13 is 1 mod 12, 17 is 5 mod 12, 19 is 7 mod 12, and 23 is 11 mod 12. Similarly, minus 11, minus 7, minus 5, minus 1 also forms a reduced residue system mod 12. So that's the basic understanding. Through an example, we have seen what is a reduced residue system. Now, couple of properties that are important here are these. So first one is if R1, R2 till R phi n forms a reduced residue system mod n, and n is greater than 2, then sum of all the Ri's will be congruent to 0 mod n. What is the meaning of this? If you take the same example as before, R12 was coming out to be 1, 5, 7, 11. Take the sum of all these Ri's. It is becoming 1 plus 5, 6 plus 7, 13 plus 11, 24, which is congruent to 0 mod 12. So that is the property that is being said. If this forms a reduced residue system mod n, then the sum of all of these reduced residues would add up to something that is congruent to mod n. zero mod n, right? This is pretty obvious. The reason why it happens like that is obvious because these are the numbers that were co-prime to 12, right? The remaining numbers of that set were anyway not co-prime. So if you add up all of them, it anyway adds up to something that is 0 mod 12, right? So these also must be 0 mod 12 because the other ones add up to something that is 0 mod 12. You can try it out and see if you are understanding this property. The next property is if R1, R2, R phi of n is a reduced residue system mod n, then and a is an integer such that GCD of a and n is 1. So a is any integer that is co-prime to n. Then if you multiply each of these with a r1, a r2, a r phi n, all of this also forms a reduced residue system mod n. So as long as you have a number a that is co-prime with n, then you can take a reduced residue system mod n and multiply each of those residues with a, and you'll still end up getting a reduced residue system even after that. So that is a very important property. Now let's look at some more properties. We had stopped at property number 10 earlier, if you remember. So property 11 is this. Suppose GCD of A and M is 1 and B is an arbitrary integer. B is an arbitrary integer. Then we have the following. First, if C1, C2 till Cm form a complete residue system mod M, then we can say that A times C1 plus B, A times C2 plus B, and so on till A times Cm plus B is also a complete residue system. So what is this? Basically, C1, C2, Cm are all the possible remainders when you divide something by m. So it's a complete residue system. And if you have a number a which is co-prime with m and b can be any number, then if you multiply with AC1 and add a b, AC2 plus b, this still forms a complete residue system. This also covers all the possible remainders when you divide it mod m. This is similar to the second property, which we have already discussed, where we said if R1, R2, R phi m is a reduced residue system mod m, then A times R1, A times R2, A times R phi m is also a reduced residue system mod m. The only condition is A and M have to be co-prime. In both of these, A and M have to be co-prime. There is no restriction on B. B can be any arbitrary integer here, right? So we can basically say that we can find several different residue systems, build it on top of an already existing residue system, right? The next property that we'll look at is this idea. Suppose A and M are co-prime to each other, the GCD is 1, and B is an arbitrary integer. B is an arbitrary integer. Then there exists an integer x such that a times x is congruent to b mod m. So we have to prove that there exists an integer such that a times x is congruent to b mod m. So the way we do it is this way. So if you take for any complete residue system C1, C2 till Cn, this is mod m. We know from the previous property that a times C1 minus b, a times C2 minus b, and so on till a times Cm minus b mod m is also a complete residue system. Right? Because the question itself has said that GCD of A and M is 1. So we are just using the property that you multiply A with all of these residues and plus or minus a B. That is an arbitrary integer. So this still forms a complete residue system. So that means, so there exists I such that A Ci minus B should be congruent to 0 mod M, right? Because it is a complete residue system for mod M, that means 0 must be part of the residues, right? The residues could be 0, 1, 2 till m minus 1. So there must be some I such that this is happening, which means that there must be some I such that ACI is congruent to B mod M, right? So X is equal to Ci. There is an X where X is equal to Ci such that this equation is satisfied, right? Basically, we are saying that there is an integer x such that ax is equal to b mod m. We are using the property of a complete residue system. Now, we'll do a special case of this equation. If am equal to 1, we know there exists x such that ax is congruent to b mod m. And in the special case, if b equal to 1, we have a situation where ax is congruent to 1 mod m, right? Any x that satisfies this relation is called the inverse of A mod M. It is called the inverse of A mod M because when you multiply A with that X, the product becomes 1 mod M, right? So in some sense, X is like A inverse, or you can even write it as 1 by A mod M, right? So any X that satisfies this relation is going to be called the inverse of A mod M. And because this relation is true for some X, the inverse definitely exists, right? There is one A inverse satisfying 1 is less than equal to A inverse is less than M, right? So the inverse mod M has some nice properties that we'll be using later. So let's list down some of these properties. So suppose A and M have GCD 1, similarly B and M are also co-prime to each other. Then if A is congruent to B mod M, it implies that 1 by A or A inverse is also congruent to 1 by B mod M. And this relationship works both ways. If 1 by A is congruent to 1 by B mod M, then A is congruent to B mod M. Similarly, the second property is if A and M are coprime and B and M are coprime as usual, 1 by AB is congruent to 1 by B into 1 by A mod M. So this is the inverse of AB, and this is the product of the inverses of A and B, right? This is one relation, and the other relation is 1 by A plus 1 by B is congruent to A plus B by AB mod M. So these relations are only true if A and M are coprime and B and M are coprime. And you can verify these two relations by checking with some examples. So for example, let's take a few examples and see what is happening. So let's say we have the set 0, 1, 2, 3 mod 4. This is a complete residue system for mod 4, right? So now think about it. For A equal to 1, what is the inverse of A? What is 1 by A? So inverse of it is itself, I think, right? Because 1 into 1 into 2 gives 2 mod 4. 1 into 3 gives 3 mod 4. 1 into 0 gives 0 mod 4. So 1 is the inverse of 1 here, right? For 2, if you think about it, 2, what do you multiply with 2? If A is 2, A inverse is what? A inverse will be, if you multiply it with 3, you get 2 mod 4. So if you multiply with 1, 2 into 3 is 6. So 2 mod 4, 2 into 2 is 4, 0 mod 4, 2 into 1 is 2 mod 4 again. 2 into 0 is 0 mod 4. So there is no inverse for 2, right? Right. Here there is no inverse for 2. For 3, do we have inverse? 3 into 3 is 9, which is 1 mod 4. For A is equal to 3, A inverse is also 3. But for 2, there is no inverse in this set, right? Unless I'm making some mistake. Yeah, there is no inverse for 2. Okay. The idea is you should be able to find inverses by following the logic that AX should be 1 mod M. Mod M. The reason there was no inverse for 2 is because 2 and 4 are not having GCD of 1, right? The condition under which we had said that inverse exists was what? We had said that if A and M is 1, then there exists X. There exists X such that AX is congruent to 1 mod M, right? So notice that our situation is failing for 2 because 2 and 4 is not 1, right? GCD of 2 and 4 is 2. So in that case, it's not necessary that you will have an inverse. But GCD of 1 and 4 is 1. GCD of 3 and 4 is 1. So in these cases, A inverse is 1. And here A inverse is 3 and so on. So hopefully you have understood what this inverse idea is. Now we look at a couple of theorems that are super important, especially from the point of view of Olympiad problems. The first one is Euler's theorem. Euler's theorem. This says if A and M are co-prime to each other, then A power phi of M is congruent to 1 mod M. Okay, so this is Euler's theorem. So the way to prove this is pretty simple. You can take any reduced system, R1, R2, R phi M, mod M. This is a reduced system, mod M. Since A and M are co-prime with each other, that means that AR1, AR2, AR phi M is also a reduced residue system. Also a reduced residue system mod M. This is one of the properties that we saw for reduced residue systems, right? So this is a reduced residue system. So let's think about what happens if we multiply all of these, right? So multiplying all of these, you will get AR1 times AR2 times AR phi M. So this will become A power phi M, and the product of R1, R2 till R phi M, right? Now we know mod M, right? Now we know that R1, R2, R phi M, all of these numbers are co-prime with M, right? So the product of these numbers will still be co-prime with M, right? So because this number R1, R2, R phi M, this product has GCD with M is 1. The GCD of this number with M is 1 because R1, R2, R phi M are all by definition co-prime with M. So the product total is also co-prime with M. Therefore, we can now cancel from both sides. This side is becoming what? A power phi M, R1, R2, R phi M. We can cancel A power phi M and A power phi M from this congruence, right? And what we will get here is simply 1. Okay, I'll just write it on the next screen. So what we are doing is this. We take R1, R2, and R phi M, right? And each of this is congruent to what? R1 mod M, R2 mod M, R phi M mod M, right? Now we multiply all of them. On the face of it, this is looking like this. R1, R2, R phi M is congruent to R1, R2, R phi M mod M. It seems like we have done nothing, but actually it is quite important here because R1, R2, R phi M was a reduced residue system mod M. We know that AR1, AR2, AR phi M is also a reduced residue system mod M because GCD of A and M was 1, right? So the product of these residues, it is the same residues that are appearing here since both are the same reduced residue system mod M. It's just that the order could be changed. AR1 could correspond to this and AR phi M could correspond to this, but these are the same residues and part of the same reduced residue system, right? So instead of these products, we can write this as simply AR1 times AR2 and AR phi M here, which becomes A power phi M and R1, R2 till R phi M here, mod M. And now because the product of these is co-prime, you can cancel this on both sides easily. Cancellation law applies if the numbers here are co-prime with M, right? And we know they are co-prime because we have taken this as a residue system, reduced residue system. So we get directly A power phi M. 1 is congruent to this mod M, which is what Euler's theorem states. So one is congruent to this modem. That is the condition of Euler's theorem. Now, let me just restate it once more. Euler's theorem. If GCD of AM is 1, then A power phi m is congruent to 1 mod m. Then we come to Fermat's little theorem. Fermat's little theorem. This theorem says if P is a prime, if P is a prime and P does not divide A, then A power P minus 1 is congruent to 1 mod P. So actually, Fermat's little theorem is a corollary of Euler's theorem only, because if you take M as P in Euler's theorem, what will happen? It will be A power phi of P is congruent to 1 mod P, right? And phi of P is P minus 1. So you're getting Fermat's little theorem from Euler's theorem, right? So this is a corollary direct consequence of Euler's theorem, as long as you know that Euler's totient function for a prime is P minus 1. Phi of P is P minus 1, right? Now, finally, we have Wilson's theorem. That is also sometimes very useful. So this theorem states that if P is a prime number, then P minus 1 factorial is congruent to minus 1 mod P. P minus 1 factorial is congruent to minus 1 mod P. The proofs for Wilson's theorems are quite standard, and you will find it in many standard textbooks. You can check it out. I just wanted to conclude with this theorem for this session. The whole session had a lot of theory. I'm sure it is a little overwhelming at this stage. What we will do is we will do a lot of problems now in the next class, next couple of classes. We'll do a lot of problems which will cover all of the applications of these properties. So the next couple of classes will be about problem solving, and hopefully that should get you more comfortable with applying the concepts that you have learned today. So keep in mind, we started with exact division, then we moved on to prime numbers, and today's class was about congruences, reduced residue systems, complete residue systems, properties of congruences, inverses, and finally the three theorems: Fermat's theorem, Euler's theorem, and Wilson's theorem. Hopefully you have understood the ideas. The next couple of sessions will be about applying them into problems. So that will help you consolidate what we have learned so far. That's all for now, and I'll see you in the next class.